Okay, here we go. So I am going to share my screen, and I think I'm getting good at this. Great. Oh. And now I'm going to go to full screen. Good. Can everyone see the cover slide and only the cover slide?
Yes, sir.
Great. Okay. By small steps to the stars. Okay, here's the plan. I'm going to be giving the next lecture and a half. So the 2:10 to 3:30 today, and then the first 40 minutes of the lecture on Wednesday. I think we're doing fine, and therefore I think we can go at a deliberate pace to make sure that everybody is following along and no one is left behind mystified. I may recommend that Aaron and Jake may want to do a little bit of a poll to gauge people's impressions of the pace of the course, and I can make adjustments throughout. The first half of the semester will largely be covering technical material from the computer, maybe a little bit of work from handwork from the iPad as a surrogate for a Blackboard, which we don't have access to here. And then the second half of the course, we're going to have some really terrific technical lecturers. I'd like to get back Scott Kemp from MIT, who's a real expert on centrifuge technology, the history of it, the implications for nonproliferation and global security. Scott played a very significant role in during the Obama administration, during the negotiations with Iran for the nuclear deal. And so he has lots of interesting stories to tell us about as well. I also would like to have Rebecca Abergel or someone else come talk to us about reprocessing technology, because chemistry was never my strong suit. And there are people who know actinide chemistry very well and can have a knack for being able to explain it in a very transparent way for non-practitioners. Okay, so today, what I want to first do is do a little bit of overlap with what we did last time, just to reinforce a few of the basic ideas. I'm pretty sure I know exactly where we stopped, and then we'll go forward from there. So as always, at the end of each lecture, I try to leave a toolkit of a few important numbers that you should emblazon on your forehead, just a few of them that are useful in doing simple calculations. Here, of importance for you is the definition of a kiloton in MKS units, and then the relationship between the language, atomic nuclear language of electron volts, and then things that we deal with in the ordinary world in MKS energies in joules and so forth. Okay. We mentioned that atoms are on the order of 10 to the -8 centimeter. The atoms are mostly empty. They're a very diffuse cloud of electrons. And in very heavy nuclei, those electrons are actually traveling relativistically. They are on the order of, about 100 times smaller than the wavelength of light. So they're not something you can see even with an ordinary microscope. The positive charge in a neutral atom is much smaller than that by another 4 orders of magnitude. And that tends to be on the order of, let's say, 10 to the minus 14 meters or 10 to the minus 12 centimeters. We name a convenient unit for measuring atomic nuclei as the Fermi, named after Enrico Fermi, is 10 to the minus 15 meters or 10 to the minus 13 centimeters. Atomic nuclei go from the proton, which is on the order of a Fermi in size, to the radius of a lead nucleus or uranium nucleus that might be 7 Fermis or so. And details inside the nucleon are not germane to this course, although that's the kind of thing I do and get quite excited about. Okay, we talked about Rutherford and the discovery of atoms. We mentioned that, and we'll go back into the whole thing about the chart of the nuclides and the value of stability. But everything that has the same number of protons, an element, will behave the same chemically, but in most instances, most of the nuclei in the periodic table can actually have multiple, multiple isotopes. In other words, they will have not simply one, but most often 2 or 3 or 4 or more species of the same proton number, but slightly differing neutron number. And this becomes terribly important in our course for lots of reasons. Even when you get up to lithium, for example, you can have you can artificially make even more exotic ones, but you actually have these 3 either stable or long-lived isotopes of lithium with 3, 4, 5 neutrons accompanying the 3 protons. Hydrogen itself, very importantly, has 3 isotopes, 2 stable, 1 unstable. So most of the hydrogen in the world is just protonic hydrogen. Out of seawater, very fraction of a percent, you can get deuterium, which is doubly heavy hydrogen, and then tritium, which has to be made. It's artificial, but has a half-life. We'll talk about half-lives later on in the lecture of 12.6 years, and is incredibly important in this business. We mentioned also that unlike atoms, nuclei, the density of nuclei kind of saturates. In other words, if even though one should not think about atomic nuclei as gluing ping pong balls together, the fact is, if you have a very large number of ping pong balls and you start gluing them together and making a larger and larger sphere of the thing, you will notice that the radius initially will grow quickly, and then the radius will only grow more gradually, simply because the radius is going like the cube root of the total number of nucleons in the nucleus. For already by medium weight nuclei, the density of atomic nuclei more or less saturates. In other words, the internal density, number of nucleons per cubic Fermi in a calcium nucleus is not terribly different from that in a gold nucleus, uranium nucleus, carbon nucleus. Okay, so it's nuclear matter. It tends to be not very compressible. Nuclei tend to have a sharp edge. Reactions really only occur, and the nuclear force is short range. So it's only when a proton and an atomic nucleus, or a neutron and atomic nucleus, or 2 nuclei get within approximately 1 Fermi of one another that they will actually experience the strong force and fuse or scatter or do something like that. Okay. Now, here was the interesting thing. And maybe what I will do is look at this slide here. We'll talk about the discovery of the neutron in a few slides. But interestingly, the mass of a proton and the mass of a neutron are almost the same, but differing by about 1 part in 1,000 or so, a little bit more than a part and a half per 1,000 or so, with the neutron being slightly heavier. This was a very interesting revelation for the nuclear physicists in trying to understand the composition of nuclear matter and the nature of nuclear physics, why there should be two particles, both strongly interacting, one charged, one not, but not identical in mass. And interestingly, it wasn't the charged particle was heavier. One might think that the internal Coulomb energy would add mass to it, but in fact, it was really the neutron, which was slightly the heavier of the two. The atomic electron is almost 2,000 times lighter, 1,836 times lighter or so, like that. As we mentioned last lecture, here is, I think, for the next lecture or so, when we get into understanding decay, nuclear decays, how nuclei can fall apart, how they decay, the reactions of nuclei, how you can put nuclei together, or proton or neutron bombarding a nucleus to make a different nucleus, or two nuclei merging to form a new nucleus, maybe plus other reaction products. You'll have to learn a little bit, you'll have to develop a little bit of familiarity with the gymnastics of calculating how exothermic or endothermic these reactions are, i.e., when you have a reaction or a decay, being able to calculate how much energy is released, because that's the whole name of the game of nuclear power and nuclear weapons, comes from this, these very, very, very slight differentials in binding energy of atomic nuclei. Now, we mentioned, and I think we got a little bit beyond this after this point, that where can you go to find out these numbers? Well, we'll go back and look over again in the National Nuclear Data Tables, the chart of the nucleides, which is incredibly useful and fun to just kind of meander around in. Many of you are practitioners already and are very familiar with nuclear data, more so than I am. But here's the key thing when we get into the issue of binding energies. We define the one atomic mass unit, which is a very useful thing to define in how one quantifies the mass of an atomic, of an atom or an atomic nucleus, as 1/12 of the mass of a carbon atom. Atom meaning not only the nucleus, but the 6 light electrons around it, which add about another 3 MeV of energy, 3.6 or 3.3 MeV of mass to it. Now, this is a mysterious thing, and why it is that if I take 6 protons and 6 neutrons and put them together, I get something which weighs less. And last time we did a little bit of a quiz, and we asked the question, what weighs more, the 6, the 12 unbound nucleons or the bound carbon-12 nucleus, or 4 unbound nucleons and a helium-4 nucleus, i.e. an alpha particle. And we were reminded that, in fact, it is the case that the unbound system weighs more. And this is rooted in Einstein's special relativity of the equivalence of mass and energy. Given that something is bound, That means to say that these nucleons somehow had to give up energy in order to be bound. The either collisional or the emission of a gamma ray or whatnot when you take individual nucleons and they end up being a bound state. And in taking away energy, you know, the rest mass of the product is lower. And we define here what we call a Q value, which is simply the sum of the initial masses in either, for example, a reaction or a decay. In the case of a decay, it just starts off with one particle. In the case of a decay, you end up with multiple particles. In a reaction, you can go A plus B going to C plus D. You can go A plus B plus C plus D plus E, whatever. But in any case, initial state mass, final state mass, subtract them, and that, if it's positive, you got energy release. If it was negative, it actually took energy to make that thing happen. Now, here there are three ways one normally talks about or that you will run into in compilations of masses, tables of masses. The one you will see in the chart of the nucleides is in what's called mass excess. But you will also see masses sometimes listed in AMU. And as I think I mentioned before, I actually had to give a class summarizing a lot of this stuff for a former student of ours who several people here remember, Jonathan Lear, who's a PhD student in history. And I had to give sort of the best of the lectures from one semester course all in 90 minutes. And I actually gave a lot of this stuff, and I actually forgot what I mentioned in this class versus what I mentioned in his class last week. But you can think of it this way. If you have a classroom of students, you say, well, Sean is 5'10½", and Elizabeth is 5'6", and here is Sayed, who's 6'3", and here is Bob, who's 5'4". You can either list the numbers absolutely. You could say, okay, take an average, you could say an arbitrarily chosen standard. In this case, we're using the International Union of Pure and Applied Physics, have designated the carbon-12 nucleus to be the standard nucleus, which is bound, but therefore we'll just simply take 1/12 of the mass of the carbon-12 atom to be the definition of the AMU. And you could say, if we designate 5'6" as being a quote unquote standard, arbitrary but standard height of a human being, you could say that Elizabeth is 0.96, Sayed is 1.11, Sean is 1.07, something like that. So you could this is the case of listing masses in AMU. The equivalent of talking about mass excesses is to say, well, if the standard human being is 5'6", I will call Sean 4.5 inches. I will call Sayed 7 inches. I will call Elizabeth minus 0.5, and Bob is minus 2. So that's the equivalent way of thinking of mass excesses, which is simply the difference of that mass minus the mass of a particle of that atomic weight, which had exactly the same binding energy as carbon. You may say, why did they do this? As you'll see, the binding energy for very large nuclei, in fact, gets to be a large number, but simply looking at the differential between that and an atom which you designate as being, quote unquote, having the standard binding energy, i.e. even a carbon-like binding energy, keeps the numbers small and tractable. And the nice thing is, the 5'6" simply averages out. If I calculate, I say, well, how much taller is Sayed versus Bob? You could say, well, that's 73 inches minus 64 inches, 9 inches. But if I do the same calculation with height excesses, I get the same answer because the average value cancels out. So when you actually go to calculate Q value, you can just simply go to the chart of the nucleides, and we'll look at this one more time, and add and subtract mass excesses, and you've got it nailed. Okay, there's a table of masses of some nucleides, and when you first look at this, you notice something rather interesting. This may be a touch small, but I hope you can read it. Well, there's our friend carbon-12, and listing the atomic masses here in atomic AMU, sometimes called AMU, here it's simply called U. By definition, it's 12.0000, okay? Now, if I look at the nuclei lighter than carbon, if I look at boron 10, it's 10.0129. So it's a number like 10, but slightly larger than 10, just a little bit. Now, there's no question that it's a bound nuclei. It's a bound system because it's an element. We find it, we use it, we make things of it. So it's a bound system. But what it means to tell you, since this number is slightly larger than the number 10, is that it is indeed bound, but the binding is not as tight as in carbon. Now, very quickly, notice when you get up to when you get up to O16, for the first time, you see that the atomic mass is less than the number 16. It's 15.9949. It's bound, but now you actually say, on the average, the binding here is slightly more than 12. And this is giving us a hint into something which is going to be terribly important for this course. In fact, I call it the money slide. It's the one important thing in this course you're going to see in a slide in just a few minutes here. Now, as you go up and up and up, you actually find that this thing is not like, 16.999 instead of 17, but the difference actually becomes quite large. Here you have krypton 95, and the atomic mass is 94.9, so it's a full 0.1% more tightly bound than the carbon standard. Then an interesting thing happens. If you keep going up and up and up, all of a sudden you find that here you are, for example, at thorium 232, we're back to the old situation where the atomic mass is actually larger than the integer. It's 232.0382. So in fact, yeah, it's bound because it exists. We dredge it out of the earth. Of course, it's bound. But you actually see that the binding energy is slightly less than that of the carbon standard, the binding energy per nucleon. Otherwise, this would have been, if it had been exactly the same as carbon, it would have been 232.0000. So here's the interesting thing. We end up with things with more poorly bound. Then you get up to things which are very tightly bound. They don't show you anything here in the iron region, but those are the most tightly bound regions of the nuclei. And then it starts sagging off a little bit, and there's a crossover point here where all of a sudden, somewhere between lead and uranium, where the binding energy per nucleon is, again, less than carbon. So we'll tease out the significance of this in just a minute. Okay, we looked at the the chart of the nuclei here. Um, let's go live and get familiar with this, play with it, just rummage around, look at things, hover over with a little hand. Let's take a look at iron 56, for example. Where's iron? Here we are, 60, 59, 58, 57, 56. We'll click on iron 56. Now you still can't see that very well, but if you hit zoom, boom, there you are. So now you've actually taken that thing and expanded it into a readable form, and you have a little box down at the bottom. And you actually see that the binding, the mass excess is a whopping minus 61 MeV. And given that there's 56 nucleons in iron 56, that tells you that there's about an additional MeV per nucleon meaning sum of protons and neutrons, than there is in carbon. So that tells you the iron is actually exceptionally well bound. And I can, unfortunately, if you just hover over without clicking, you can see all kinds of interesting things here. Iron 56, anything that's black is absolutely stable. And they actually, there's a little key here that tells you, oh yes, over here, the color and the lifetime. So things which are very dark colors have very, very, very long half-lives, and things as they get lighter are very, very, very short-lived. I'm abysmally colorblind, so this is of lesser utility to me than it is to you. But I can tell there are different colors. Okay, and and there's lots of information here that is not important to you, but if you're a nuclear engineering major and you love nuclear physics, Lee Bernstein will help you love nuclear physics, then this is a absolutely fascinating database here. Okay, on we go. Whoops, we have to get rid of this. Here we go. Okay, for those who are not physicists or nuclear chemists or generally don't deal with this, as practitioners, the way to think about the valley of stability is just think of it as a physical valley. We talk about the chart of the nucleides. There it is, just a little snapshot of it. And you see that the black nuclei are the ones which are absolutely stable. And the ones that are absolutely stable are, there's, as I say, for any given Z goes up, proton number goes up, neutron number goes to the right. There are a few, but not an infinite number each. There might be 2, 3, 4, 5, 6 or so stable isotopes for any given element. But what's interesting is that all the nuclei which are either stable or bound for a significant period of time all lie on something that looks like kind of a very thin peninsula. Actually, this is a valley. And if you take a crosscut here, if I say, let's look at all the elements that have A of 109, or let's look at all the elements that have A of 40 down here, and I make a diagonal crosscut here and say, what's the mass of these nuclei? You would say, well, there's 40 nucleons, no matter where you are in this crosscut. Here's 140. But what you actually see is something that looks indeed like a valley. The one down at the bottom of the valley is the most tightly bound. It has the lowest mass. And then I start crawling up the walls of the valley. Here we are on the proton-rich side, cerium, praseodymium, neodymium, oh God help me, PM. Okay, samarium, europium. On the neutron-rich side, you have lanthanum, barium, cesium, xenon, and iodine, and you actually do get this kind of bowl-shaped structure. Ideally, it should be in simplistic theory, it should be a nice parabola. Sometimes it is, sometimes it isn't. Here's one which is definitely not a parabola. It actually looks like a V. It's much sharper than a parabola. This is the odd even nucleus here. This is praseodymium, cerium, lanthanum, barium, so forth, like that. Okay. Okay, so let's actually do a calculation. My Los Alamos colleagues know very well one of my dear friends, Mark Chadwick, who is, I'm trying to think whether he is the grandson or the grandson, I think, of James Chadwick, who, a very famous physicist, nuclear physicist of the 20th century, who discovered the neutron. Mark was actually on the staff at Livermore with us up until the mid-90s, and we were very sorry to lose him, but of course he stayed in the family, went to Los Alamos, where he's had a brilliant career, very, very distinguished nuclear theorist, and very much involved in the nuclear weapons program down there. So until 1932, people were mystified about why things that behaved elementally the same could be found with masses which looked suspiciously like they were separated by simply one proton mass. And they say, well, what's going on here? How can this happen? Finally, Chadwick was the one who kind of elucidated the issue. He took a radioactive source of polonium, which emits alpha particles. We'll talk about decays in a minute, but here are these alpha particles coming out with approximately 5 MeV of energy. He puts up a thin beryllium sheet, and the alpha particles impinge on it. Some of them will actually undergo a nuclear reaction. So you have helium-4 plus beryllium-9, giving rise to carbon-12 plus, lo and behold, a free neutron. Now, they did not know about neutrons. I'm not quite sure the thought process. I don't know the scientific history of whether he was looking for this or suspected something, or this was hypothesis driven or a bit more of a fishing expedition. But then he puts up a very thin piece of paraffin, which is highly hydrogenous material, i.e. lots of protons there. Things of roughly equal mass are most effective at taking energy out of the incident particle and put it into the knock-on particle. In case of the proton and neutron, it's essentially, since they're almost equal in mass, you can have a neutron undergoing a collision with a proton and knocking the proton forward and with the same energy, and the neutron will remain effectively at rest. But a charged particle like a proton can easily be seen in a Geiger counter. And sure enough, when he puts up this arrangement like this, here you could, there was simply nothing here. The Geiger counter did not see anything when you took away the paraffin, but when you put in the paraffin and the neutrons knocked on the proton, you were seeing these large regular signals, which was evidence of the fact that there was this ghostly particle of approximately equal mass to the proton, and then he declared the discovery of the neutron.
Carl?
Okay.
I can answer why he was looking for this. Before this, Pauli had proposed the neutrino in response to some experiments from beta decay. He actually proposed what he called the neutron, but what was actually the neutrino. So there was sort of a miscommunication and sort of a confusion between Pauli and he proposed this really nice neutrino mechanism. It was actually parodied in Copenhagen Faust, which is a play that Delbruck wrote for the Copenhagen meetings. And at the first meeting in 1932, Chadwick came in, he played Wagner in the play, and experimentally demonstrated the neutron, not the neutrino. Pauli looked maybe like he was wrong. He was actually right. There is a neutrino. And later on, that was shown by Fermi when he came up with the beta decay equation.
Did he actually have an experiment on stage?
No, Chadwick had done the experiment, but then went to
Okay.
Copenhagen at the behest of Bohr.
Okay. Anyway, here we go. So we have a what is the gain in energy between the initial state and the final state when I take helium plus beryllium and make carbon plus a neutron here. I go to the Brookhaven database. I go to my other table here where they're actually listed in AMU, and 4.0026 plus 9.01218 minus 12 exactly minus 1.008665 multiply by the definition of an AMU, and you come out with a small positive number of something close to 6 MeV. These are now sources which are used in every physics lab and nuclear engineering department for doing student experiments and other experiments which require low neutron yields. This was there's plutonium beryllium, polonium beryllium, americium beryllium sources. Anything that emits an alpha particle that you put in close conjunction with beryllium, you can actually grind them into powder and put them together. And then this thing will just give off a steady stream of neutrons forever and ever that you can use for calibrating detectors or doing experiments or whatnot. Okay, try this yourself. Go look at other reactions and become familiar with the Brookhaven data library. All right, so here is the, if that kind of looked intriguing or puzzling to you, why you were seeing numbers with light nuclei with slightly larger or slightly lesser binding energies than carbon, then it got large and then it got small again. This is the what this course is all about. It's called the curve of binding energy. And you see for very light nuclei, the binding energy per nucleon here in MeV goes up very, very sharply and kind of plateaus. There's a high plateau. It's about 8.5 MeV per nucleon in the iron group. In fact, iron is, this has a very special role in the universe, as you actually see a lot of things in the iron group here. But then nuclei heavier than this are indeed bound, but the binding slowly trails off like this. You might say, what's kind of the generic? If you wanted a sound bite, why does it rise up, reach kind of a plateau, and then sag off? Very simply this, for very light nuclei, they tend to be kind of all skin and no volume, and you might just suspect just from physical intuition, that nucleons on the surface of a nucleus will be less bound than the interior. And therefore, if I make atomic nuclei which are larger and larger, then that's a more favorable, there's less surface to volume ratio or more volume to surface ratio. So the binding per nucleon will increase. Now, at some point, all of a sudden, these things are not only becoming larger, but they're also becoming more highly electrically charged, and the Coulomb repulsion, the Coulomb energy, here works to, in a sense, to provide an unbinding term, and therefore, as you go up in mass here, the binding will trail off like that. Now, that raises another question. We don't want to get into too much. This is not, as I say, not a 101 course. You just want to understand general features. But you might say, well, why is it that nuclei want to have, at least light nuclei? You actually find that the slope here is sort of, one-to-one. So sort of the light nuclei up to calcium tend to be, essentially 1-per-1. N equals to Z is the most stable. And then it tends to sag off here, and that's for the same reason. The nuclei which are most stable are the ones that tend to be a little more neutron rich. In other words, if you have to have a certain number of neutrons and a certain number of total number of neutrons and protons, you're better off with fewer protons to be more stable. Now, that begs the question that I raised, what is trying to enforce symmetry in the first place? Why can't I have an atomic nucleus that is 140 neutrons and no protons? That doesn't exist. I can't have 140 protons and no neutrons. That doesn't exist either. There is nuclei want to be in this tight band, and if I deviate from the band, the energy is kind of going up quadratically. That gets into something we don't need to get into in this course, which is a symmetry energy term in the atomic mass formula. And it has to do with the fact that the protons and neutrons are both filling up their own shell structure of orbitals in neutrons and protons. And if one then begins to unbalance them like this, there is you actually suffer a penalty for them being unbound. So they tend to be on the balance equal and slightly more neutron rich for heavier nuclei. Detail of no importance here, but obviously very important to in 101. So let me blow this up a little bit. And this is what I call the money slide. The whole reason this course exists, this has to do with proliferation of nuclear weapons, nuclear power, all this kind of stuff here, is only due to one reason, and that is that this curve is not flat. If this curve were dead flat, you'd be taking another course right now, and there would be no nuclear reactors in the world. There'd be no nuclear weapons, because this is, in a sense, two stories going on here. If you see something like this, a binding energy curve, which is low, goes high, and goes low like this, there's two ways of making money. Okay, one is to say, if I take two light nuclei and put them together to make a heavier nuclei, the binding energy goes up, which means the nucleus up here is going to be more tightly bound. That means in making that new species, I had to release energy. So that's one way of releasing energy, is fusing light nuclei. The other way of profiting from this binding curve is to look at the things that we care about in this course in the mass 230, 240 region, your fissionable nuclei. Notice they have about 7.6 MeV of binding energy. Now, simplistically, let's just take something that's mass 240 roughly, is a nice round number, and I split it into two parts of 120 each. They, in fact, tend not to come out exactly in two equal parts. But if I now look at 120, you see that the binding energy per nucleon is 8.5. So I went from 7.6 to 8.5. On the average, there was an additional 0.9 MeV of binding energy associated with the difference between 220 mass species and one 240 species. So 0.9 MeV times 240 is about 200 MeV. That's a lot of energy. So that's the name of the game. If I break a large nucleus in half, because the final state, the two main fragments are much more tightly bound, I have gained energy out of that thing. So this is why I call it the money slide. And modern day nuclear weapons make use of both these phenomenon of fission and fusion. Okay. One more thing here, and I think we will probably move on to, we'll get in already into another lecture. At some point, I'm going to go grab water. My throat is, I'm actually losing my voice here. I think you know enough from your, even if you've not taken 7 series or anything like that, here, if you're undergraduates or if you've not taken a great deal of basic science, I think you know enough from your basic studies, even in high school physics, to know that when you look at the atomic spectra of atoms, that in general, you do not see a continuum of frequencies, that you see, if I do a simple experiment you probably did in high school physics with a prism, a quartz lamp that might be a xenon flash lamp or some other neon flash lamp, something like that. Then you have either a grating or a prism, and then you have a photographic plate or a ground glass screen. You will actually see individual lines. And this bespeaks the fact that quantum mechanically, a bound system such as an atom only exists with electrons in orbitals of particular energy. And energy is either absorbed or released when these electrons make transitions between one bound level and another. And in the case, the simplest case of an atom, which already when you look in detail is plenty complicated, but the basics of it are very simple. When you look at even the Bohr picture of an atom or the simplest real quantum mechanical treatment of an atom, you have transitions. If I make a plasma or an arc lamp of hydrogen, you will actually see lines that go from higher excited states to the ground state. These transitions are actually in the ultraviolet. Don't see them with the naked eye, the Lyman series. The Balmer series and some of the Paschen series you actually see optically and so forth. Nothing new here. You've seen this, don't want to dwell on it. The only point I want to make is that atomic nuclei are very similar. It's a quantum mechanical system. The protons and the neutrons in the system, you do need to do most simplistically, you make a kind of a square well potential. You can solve Schrodinger's equation and get bound states. Actually, the nucleus is a much more problematic situation to calculate than atomic nuclei because the force is so strong. But you can go ahead and then calculate this. And once again, you actually find that atomic nuclei, the spectrum of atomic nuclei is also discrete. There are discrete levels. And once you get that, then this adds a lot of richness to the problem. In particular, in gamma decays, you will normally not see a continuum spectrum, but you will normally see discrete gamma lines associated with that. Okay. Something I just cribbed from the web. Interestingly, the things that we directly experience, either that we see, we've evolved to actually see with our eyes over a very, very, very narrow part of the entire electromagnetic spectrum that goes all the way from radio waves up to very, very, very high energy gamma rays here. And there is our toolkit so just here are the things to remember in our new language, atomic and nuclear language, where we speak of electron volts or mega electron volts. The electron is about half an MeV, proton and neutron close to a GeV, very slightly different. And then what we define as an atomic mass unit, just picking carbon-12 somewhat arbitrarily to be the standard, is about 7.5 MeV average binding energy down from the bare mass here. Atomic nuclei tend to be on the order of several Fermis in radius. Again, several orders of magnitude, 4 orders of magnitude smaller than an atomic nuclei. And last thing here, people say, what's the value proposition of nuclear energy? I think we're all very pleased that the new administration is taking, kind of the all of the above approach. If you're serious about climate change, you want to be serious about nuclear power as well. Very good mnemonic here. If you look at the fuel supply required for a gigawatt power plant, it's a very good standard size power plant. One reactor in a nuclear plant, typically there are 2 gigawatt scale plants, reactors here. The coal required is 2.5 million tons. That's 25,000 rail cars. No one likes coal. I don't like coal. Okay. Oil, it would take 11 super tankers, these things 1,000 feet long, full of oil to do the same trick. Fission energy would take about 1.5 rail cars of sort of low enriched uranium. Fusion, deuterium for the deuterium-tritium reaction. Now you can crack doing a nuclear reaction where you're cracking lithium-6. You can actually use lithium in a fusion reactor as a blanket to both absorb the energy, but it also will produce tritium in an alpha particle. So you actually can you can actually make your own fuel on the fly and feed it back into the reactor. So it's self-sustaining. Just a few hundred pounds fits in the back of your pickup truck. Get a clue. Okay. What I'm going to do is go fill up my water bottle. I will be back in 1 minute, and we will continue into the next lecture. We have half an hour left. So all right. Okay. So I'm going to I should ask if there's any questions. Was anything unclear here? Okay. Am I on, off mute? Okay, hold on here.
I had one.
Sure.
Well, when you were talking about the stability of iron earlier with the binding energy,
Yeah.
I've heard in the past that iron is the heaviest element that can be made by fusion. How like inside of a star, how do those two play together? Is that a different property that leads to that fact, or?
Okay, so that's nuclear astrophysics, and that's a very good question. Um,
You don't have to spend too much time if it would take a lengthy explanation.
Let's see. Let's see. Once you get up to iron, what happens? Yeah, that's actually a little more detailed question. I'm actually very delighted to answer it, but why don't we go offline there?
Okay, that sounds great.
Once you there's lots of bad endings that stars come to when you get up to the point where you all of a sudden can no longer make energy by fusing nuclei together, and you basically run out of fuel, and then you can end up with supernovae. But let's that's a great question. Are you a physics major?
I'm not. I just like space a lot.
Oh, cool. Great. Yes, let's actually do that, but not in the confines of the lecture here. And I'll come back to you with a crisp answer on that. Lee Bernstein also, in addition to many other things, does nuclear astrophysics, as does Rick Norman and Rick Haxton and other Dan Kaysen, other people here on campus. But yeah, it's basically due to the fact that the binding energy curve turns over there, and you just get to the point where you've burned up all the fuel and you're not gaining any more energy by fusing, and then the star can undergo a catastrophic collapse, literally in a fraction of a second. Okay, good. Let's move on.
Sounds painful.
Yeah, they're quite spectacular. It's interesting. There was the last supernova that really attracted a lot of public attention, 1987A. It was actually just 160,000 light years away in the Small Magellanic Cloud. It was a type 2 supernova. Those things actually give off more energy in like a fraction of a second than the rest of the universe put together. And 99% of I think Sterling Colgate from Los Alamos, formerly Livermore in Los Alamos, was one of the early workers in this. It actually validated. We actually saw the neutrinos on Earth in large water-based Cherenkov detectors under Lake Erie, Irving, Michigan, Brookhaven detector, and one in Kamioka in Japan that were looking for proton decay. Actually saw a burst of neutrinos that came from this thing all in about 10 seconds, and validated the astrophysicists' most cherished belief that when these stars blow up, they give out 99% of their energy comes out in neutrinos. And even as large as the optical flash is, that's small potatoes compared to the neutrino flash from these things. It's quite interesting. Anyway, that for another day. Okay, let me go back to full screen. Let's see here. Great. Great. So we're actually going to talk about, I mentioned that, I just sort of referred to the curve of binding energy as kind of the money slide, so all of nuclear power and nuclear weapons, you're basically living off what are basically differentials. Everything is bound, but the thing is they're bound slightly unequally. And it's that margin that allows you to profit. And it's a little bit, you could think of it in very, very loose terms, a little bit like the stock market. Either long selling or short selling, that's a temporal thing, that's time. But you're actually profiting or losing based on very small differentials in the value of a stock. So think of a single share of stock, So you can think of this whole business a little bit in that manner. Okay. Alpha decay. We actually mentioned alpha decay as the source of the particles that Chadwick used in this experiment. This is very common. Those of you who have taken undergraduate physics labs or nuclear engineering labs get to play with these things. Maybe they're more strict about it now, but they used to have these little things that would be mounted in a room in a little iron. It's called an iron pig there, or that you would put little discs of aluminum on it with a little battery, and after a day or so, you would take it off, and there would be some atoms there that emitted alpha particles, americium, whatnot, and you could use for experiments for calibrating detectors or doing other experiments like that. What alpha decay is a nucleus of A and Z becoming A minus 4 and Z minus 2 and emitting an alpha particle, which is a helium-4 nucleus of mass 4, charge 2. So two protons, 2 neutrons. Notice, if I didn't say it, but implicitly, the total number of neutrons and protons is always conserved. A neutron can become a proton or vice versa in different contexts, beta decay, positron decay, electron capture, and so forth. But the total number of nucleons always must remain the same. What happens here? Well, if you look very carefully at the energies coming out, it's not a continuum. These do come out in sharp lines because they're going from the ground state, which is a state of sharp energy in the parent, to a state of sharp energy in the daughter, which may be the ground state or an excited state. So you will actually see sharp lines, but you may see multiple sharp lines. Here you see plutonium-239, for example. It's an alpha emitter, and you see, you kind of see 3 distinct lines here. Americium-241, you see 2 lines. Everything in alpha decay, or most things in alpha decay, are around 5 MeV plus or minus. You see some oddballs which are about 10 MeV and some which are 4 MeV lower, but typically they're about 5 MeV. Lifetimes go from years to billions of years. And again, these are the things that you'll see when you kind of meander around the chart of the nuclei. You'll actually see what the alpha, you'll actually go back and see what the alpha decay half-lives are when you take that little hand and hover over or click on any of those nuclei up in the high mass range. Surprisingly, although I think those of you have bleached your bones in physics labs and nuclear engineering labs, your alpha emitters you always think of as being in the americium, thorium, polonium, things much heavier than lead. Alpha decay does exist all the way down to about mass 140, but those are very kind of rare animals, that you see. You normally don't think of medium weight nuclei as alpha emitters, but it does happen. Now, think of the chart of the nucleides as a chessboard. What happens with alpha decay? How does the piece move on the chessboard in alpha decay?
A bishop or diagonal?
Yeah. Which direction?
Down to the left.
Yep, exactly. That's it. So here's plutonium 240 goes to uranium 236. In fact, here actually it just shows you alpha decay is effectively 100%. It's got a 6,600 year half-life. We'll talk about half-lives here. SF stands for spontaneous fission. Some things, we'll talk about fission in a while, can just fall apart into two fragments themselves. But the branching ratio here is very, very tiny. Look at this. It's 5.7, 10 to the minus 6%. So it's like, 6, 10 to the minus 8 of the time it will fission relative to alpha decay. But this thing is overwhelmingly an alpha emitter. Okay. Beta decay. We talked a little bit about this, and let me thank Jake and Aaron for answering questions on the fly or adding commentary in the chat. Thank you guys for doing that. So beta decay here is a three-body final state. And we'll talk about variants of beta decay. Here you have a carbon-14 nucleus. We'll talk about carbon-14 in a little more detail in a while. It has an inconveniently, when you get away from the value of stability and you get nuclei which are therefore a little bit more massive, the rule in physics is that if something can happen, it will happen. If carbon-14 is heavier than nitrogen-14, it's going to find a way of becoming nitrogen-14, usually. And what happens is that it will beta decay. Carbon-14, one of the neutrons will become a proton. So it'll go from 6 protons, 8 neutrons to 7 protons, 7 neutrons. It will emit an electron. That's how the charge is conserved. It becomes one more proton, but it gives you an electron. So the total charge it remains the same. And this ghostly particle that was mentioned called in this case, an anti-neutrino. That was predicted by Wolfgang Pauli, who desperately did not want to give up on conservation of momentum. They actually saw these strange events in emulsions where particles decayed not in a back-to-back fashion, as you'd expect from a two-body decay. And his only thing is, well, there must be something off weakly interacting that's flying here in this other direction, unseen, and conserving momentum and energy. There was a problem with energy as well. And it wasn't until Reines and Cow and the famous experiment at the Savannah River reactor in 1956, approximately 30 some odd years later, 20 some odd years later, when they actually found very clean evidence for inverse beta decay, with actually detection of the neutrinos coming out of the core of the reactor. There's a story that they actually had, when the news hit, they had a gala party somewhere up in the Swiss Alps, I think, and at some very high altitude. And Pauli had a little bit too much champagne, but he was in a fine mood. And as he was sort of coming down the mountain with his arms around the shoulders of his friends, he famously quipped. He said, "All good things come to those who wait." So he had to wait 20 years for the validation, but he'd actually finally gotten his lovely neutrino, anti-neutrino. Okay, now because this is a three-body final state, if you have a two-body final state, like alpha decay, the only way of conserving energy and momentum is that they go out back to back and they both have a definite momentum and definite energy. In the case of a three-body final state, they can come out at different angles, and there's an infinite number of ways of parsing the energy and the momentum, so long as the net momentum is zero and the energy is the energy that you began with. But for that reason, since sometimes the neutrino will take the predominant share of the energy. Sometimes it will take only a minuscule fraction of the energy. The electron, which is what you normally look at, that's a charged particle, and it will bump into you. It will penetrate your skin, or it'll go into your detector. Is a smear like this, right? So it's a continuum whose endpoint is it represents the limit where the neutrino comes off with very little energy and the electron takes all of the energy. The other end of the spectrum is where the neutrino takes all of the energy and the electron takes essentially nothing. Okay, now what about beta decay? Again, this goes from fractions of seconds to millions of years or longer. It's important across the whole chart of the nuclei, and the energies are typically they can be anything up to a few MeV, but as low as a keV. In the case of tritium, I think the endpoint energy is 18.6 keV, I think. But you do find some beta emitters which give off very, very hard betas as well. Now, I mentioned that there are variants to this. For things which are neutron rich, they'll give off a neutron will become a proton. To balance charge, you have an electron and an antineutrino. If I'm on the other side of the valley of stability, if I get something which is proton rich, doesn't happen too often in things that we care about, the proton will become a neutron, give off a positron, or a anti-electron, and a neutrino, the antiparticle of a neutrino. In that case, you can also have a situation of called electron capture, where the nucleus can basically eat an electron to go down by one charge, and then you just come off with the neutrino. And so that's a two-body final state, but you don't see the neutrino. You can end up with subsequent gamma rays as well. Not important for our course. All right, chessboard again. If you think of the chart of the nuclides as a chessboard, how does beta decay move? So here neutrons are going to the right, and proton number is going up upwards. So neutrons increase to the right, protons increase upwards. So how does beta decay move on the chessboard here?
Left one, up one.
Yep. Like that. Here's something interesting that'll be very important. Let's go back here. Something that's going to be very important later in the course when we talk about fuel is where does plutonium-239 come from? It's got a half-life of 24,000 years, so you're not going to find it naturally in the Earth's crust. If you absorb a neutron on uranium-238, it becomes 239. Beta decays with 23 minutes half-life to neptunium-239 with a 2.4, where's my cursor here, 2.4 day half-life, and then beta decays to 239 plutonium, like that. So that's where plutonium-239 comes from. Okay, more on that later when we get into fuel. All right, gamma decay. I can, after any reaction, a fusion reaction, absorption of a neutron, or fissioning event, I may end up with a nucleus which is not in its ground state, but it's bound. It doesn't have enough energy to spit out a particle, but it is bound, and eventually it wants to get down to the ground state. It will emit electromagnetic radiation. And as I showed on that little cartoon before, electromagnetic radiation, it's all the same thing. You know, it's it's Maxwell, James Clerk Maxwell, right, electromagnetic radiation, but of different frequencies and different energies. In the optical case, the wavelength is, basically half a micron, or 4,000 or 5,000 angstroms, or 400 or 500 nanometers. And such a photon has about 2 electron volt of energy. In gamma decay, these are very, very short wavelengths. I didn't actually show this, but the wavelength is the speed of light divided by the frequency, or the frequency is the speed of light divided by the wavelength. The energies here are typically in the MeV range. There'll be a few hundred kilovolts, or an MeV, or 6 MeV, or something like that. And generally, these are very, very fast. Not always, but they tend to be 10 to the minus 18 seconds, 10 to the minus 16 seconds decay. There may be reasons why it gets stuck and takes a long time to decay, but typically gamma decay will be very, very prompt, very fast. Also comes out for reasons I mentioned before, just like in the case of atomic systems, in sharp lines. And that's interesting and important, because gamma spectra can be an important forensic fingerprint. So you can learn things about anything from astrophysics. When you look at stellar processes, you actually see gamma, not only atomic lines from plasmas and atoms, but you can also see gamma lines from the decay of excited nuclei from products from supernovae or whatnot like that. And so they are a very, very good, gamma spectrum are a very important scientific tool and forensic tool. Okay, yeah, there we have it here. The inverse relationship between frequency and wavelength. 30 meters being, or 10 meters being like 30 megahertz frequency. Okay, we'll talk about this a little bit in the end of the course, particularly when we get into radiation effects as well. Alpha particles carry a lot of energy. In general, you don't need to worry about them, and that's why, at least in the old days, I hope still today, students are allowed to make their own sources and use them, and then kind of throw them away in approved trash. The one exception is if you inhale, like radon, in some parts of the country geographically, where you may have some anomalously high radon coming up through the Earth's crust, through your cellar, your basement, and so forth there. If you inhale them and it sort of lodges in the atom, lodges in your lung, of course, it can do damage to your lung tissue and cause cancer. But generally, the alpha particles lose a lot of energy very quickly, and therefore are stopped in just a layer of dead skin. So the beta particles are more penetrating. They're swifter, faster. They are semi-relativistic or relativistic. And to stop them normally will require a little bit more substantial, like a 16th inch or an 1/8 inch piece of metal, something like that, again, depending on the energy. Gamma rays or X-rays can be very penetrating, and will normally the best way to stop them is with a sheet or a plate of some high Z nucleus like lead. Neutrons will sail through pretty much anything, but one of the most effective ways of stopping the neutrons, of course, is to have them knock into something of equal mass, i.e. a proton. So anything hydrogenous, water, paraffin, polyethylene, are very, very good for slowing down and stopping neutrons. Oh, it's 3:30. Okay. it's actually better to go slowly and deliberately. Please send us feedback on the pace of the course. Some of you are probably being bored to tears. Others may be in a little bit of a panic. Don't panic. We're here to help. But I get the sense we're probably going at a good deliberate pace for comprehension here. Any questions? And if not, I'll pick up and do the first 40 minutes on Wednesday.
Thank you.